who's on loan to us from Denver. We then rented him from Mohr for a little bit. So he's here to tell us about some Turán things that are very uniform. Take it away, Sam.
Yeah, so thanks, Bernard, for the invitation, and thank you all for showing up. So the next 40 minutes, maybe 45, let's see, I want to speak about uniform Turán density, and there are basically three things. So first, I like to introduce it, spend maybe most of the time to introduction, show you why is it nice, what are the open problems, what are the tough open problems. And then in the second part, I show you how to obtain lower bounds on it. Lower bounds are usually more easy, upper bounds are super hard. If time allows me, I will show you a bit how to approach this. Just give you a glimpse into it. Okay, so it's all about the following. About this. So the extremal number, extremal Turán number of n and a graph f, a small graph f. So we ask for the number of edges that an n vertex graph can have so that it's still f free. So, and we want to maximize this number. Okay, so maximizing is clear, the number of edges is clear. I consider not only two graphs, but the normal graphs. Most of the time I will speak about three uniform hypergraphs. We can in general say that is some k graph. So each edge has exactly k vertices. F3 means that you don't find f as a subgraph. You don't care about induced, only as a subgraph is fine. Yeah. And so this is the number of edges, and if we want to go to the word density, we define the density of it. So we divide it by all edges, and all edges are the number of vertices, and you choose k because it's a k graph. So in the graph case, you choose it's n choose 2. Okay, now what can be done by some averaging argument is showing that this thing is decreasing for n towards infinity. So if you have some n and you choose some smaller n and consider all subgraphs with the same, or you choose a subgraph with the same probability that has n prime for a smaller n prime graph, then it's still f3, it's a subgraph. And if you added up all of them, then they have it has exactly the same density. So there is a graph that has at least this density, and that is more or less the argument why it's decreasing. So we have a decreasing number for n to infinity. It's bounded from below by 0, means that this limit always exists. And we can define we call it the Turán density of this graph f. Good. So the easiest case is the graph case. So k equal 2, and we are in the graph case. What can we choose for f? So a choice for f could be the triangle. So basically this graph. And this is solved by Mantel and to look up in 1907. So you see it's quite an old problem, and first solutions reach back more than 100 years. In the general case of KT, it's solved by Turán, and therefore the name. It's done in 1941. So what's the solution of it? The solution, if we want the KT free, let's call it KT plus 1 free graph, the solution is the balanced t-partite graph. So meaning I choose my n vertices in exactly t sets, and I put all the edges in between everywhere. And this graph is maximizing the density, and you can calculate the values. So x k n kt plus 1 over n choose 2 goes for n to infinity to 1 minus 1 over t. Okay, so we have basically all the complete graphs now. Let's think what is the situation with all graphs. General case for an F specific graph, we can get the chromatic number, so the minimum number that is needed to color it. And in this case, let's assume it's at least 3, so that the arguments work. If it's a bipartite graph, it's getting a bit different, but it's also well known. And therefore, we have Erd H and Stone, 1943, I guess, 46. And they showed that this value goes to this if R is chromatic number. Yeah, so the graph case is more or less completely solved. So let's put here 3 and consider 3 uniform hypergraphs. So in the graph case, the first question was the triangle. The first question in the 3 uniform case is somehow the complete graph on 4 vertices. And we put all triples as edges in. And I like to denote this by this graph. So what's the Turán density of this? And you see, this is quite an old problem. And the only thing I can say to this, it's still open for more than 80 years. Oh, by the way, if you have any questions, feel free to interrupt me at any point. Yeah. Actually, if you want to get rich, or maybe a bit rich, you can try to solve this. So Erd H promised some maybe $500 US or $1,000 US. Maybe 500 for this, 1,000 for all complete graphs. Might be some nice money. But might be hard to get it.
You will get checked those
Good. So we don't know what's the uniform Turán density of this. But do we have some bounds on it? And we do. So as a lower bound, we have 5/9. So how to get this? So I like to group my vertices into 3 more or less equal sized parts. So let's call it V1, V2, and V3. And now I ask what kind of edges I want to plug into this graph. So here I have a bunch of vertices. Okay, so we say that E is an edge in 2 cases. The first case, if it contains exactly 1 vertex from each, which gives us, for example, this edge, or maybe this edge. And the second case is that this is 2 and the next one contains 1 vertex. So indices are modulo 3. So you have 2 vertices of V. 2 vertices of V3, then you have 1 vertex of V1. That should be 1. So how do edges look like this? So if I grab 2 of those vertices, I can grab 1 here. If I grab 2 of the vertices here, I grab 1 there. But I cannot grab 2 vertices here and 1 here. So does this graph contain this K4, 3? So if I choose all 4 vertices in 1 bubble, cannot succeed. If you choose only 3 in 1 bubble, you also need somehow the edge containing 3 vertices. They do not exist, so I cannot put 3 there. Meaning I put 2 here. So if I take 1 here, I cannot have this edge. Yeah. So I have to choose the other 2 here, and that gives me the problem. I have 2 vertices here and there. So this graph does not contain K43. So what's the edge density in this graph? Call it H. So we choose basically 3 vertices for each edge, meaning for each vertex I have 3 possibilities. Then I have the green edges containing 1 from each. There are 6 or 3 factorial of 3 possibilities. And I have all the red edges. So for the red edges I have 3 possibilities to choose the set. So 2 here, 1 there. And for those 3 I have basically picked this vertex in 3 possibilities given. So that gives me this. It's 6 plus 9, 15 over 27. It's exactly this 5 over 9. Good. Okay, maybe I should mention that there's an upper bound. So the upper bound is 0.5616. It uses some flag algebra methods to prove this. So that's 0.55. We are close, but we're not exact. And the conjecture is that is the correct value. Okay, so if you look again to this example a bit closer, you see that if you choose 1/3 of your favorite vertices, you can have a lot of edges. But if you choose it, for example, here, then you don't see any edges. So the edges are highly non-uniformly distributed in this graph. And that brings us to the definition of uniform Turán density. So I need only one definition for this, and this is epsilon density. So the epsilon density for hypergraph H is basically the maximum D such that each subgraph with at least epsilon, or well, the number of vertices should be at least epsilon. So for each epsilon linear fraction of vertices, I have a lower, or this density bounds is a lower bound for the density. So in this case, the epsilon density would be 0. I can choose some third vertices without any edges. Yeah. For the complete graph, it's, for example, 1.
So by density here, your edge density.
Edge density.
Okay, great.
And edge density, a number of edges divided by number of possible edges. Okay. And then we can say what's the uniform Turán density. I put here U as a subscript. Graph H. So that's the largest D, such that for all epsilon there exists sufficiently large hypergraph H, such that the epsilon density of H is at least D. Yes. And somehow I have to bring in this F, so H should be F free. And by this definition, it's clear so that the uniform the Turán density of any graph is lower bounded by the uniform Turán density. Good. So I guess you might ask now, what's the uniform Turán density of different graphs? And possibly the first question you will have is what's the uniform Turán density of this graph. I have to disappoint you, it's open. It's open and many people are interested in this solution. So feel free to work on this. But I can show you a lower bound on this. No, actually not on this. So then the next question I like to have, to make it a bit simpler, I remove one edge. The graph has, again, 4 vertices, and all the triples that are inside contain this middle vertex. So I basically have removed one edge. And for this graph, I can show you the lower bound of 1/4. So you just take a big set of vertices, as many as you wish, and between each pair you put in some arcs. And then 2 things can happen. Either you have it like here, a tournament. So you can order the vertices so that all edges go to the other direction. That can happen, or it can look like this. So you have a directed cycle. And then you say this graph, or the edge set of this graph, are all the edges that are directed cycles. So I put in this edge, assume it looks like this. I will also put in this edge, and so on and so on. So what's the density of this graph? You choose 3 vertices. The first edge, you don't care what's the direction of it, and the direction of the other 2 edges is determined by this one. Meaning that the density of this graph, we can call it H, is 1/4. And can it contain this graph? So if it contains this, I can find these 4 vertices. I consider middle vertex. This edge has one direction, either this one or the other one. But to close, or to get this edge, I have to close the cycle like this. And to get this edge, I have to close the cycle like this. And you will never obtain the last edge. So that's a construction to get this lower bound. It has density 1/4. It's K4 3 minus 3. And by some probabilistic estimations, you can show that it's almost surely unique. Each epsilon density is 1/4. Good. This case actually is solved, and it is 1/4. That's shown by Clever, Karl Wallets in 2016, so not so old, using flag algebra methods, and Reiher, Schacht solved it without the help of a computer. Okay. So I've shown you a way to obtain a lower bound in this case, and I like to spend a bit more on showing you how to obtain lower bounds. Some space here. So a lower bound for this graph. So how can I obtain one? I choose a lot of vertices again, and I order them linearly. And now I use two colors and color each pair of them. For example, I make this white, this is white, this is white. This is green, this is green, this is green. Yeah. So I color all of the pairs. And now I define what is a good coloring of a triple and what's not a good one. And so if I have three vertices, I say it is good, the color of the top edge and the color of the left edge are differently. So basically if those two colors are different, then it's a good one. And by doing so, I obtain a couple of edges. So for example, I have green red here, meaning that those three are an edge. Or this vertex, and this vertex, they are also an edge, and so on, and so on. So again, the two questions, what's the density? So if I choose a triple of vertices, example, this one, and this one, it doesn't matter what's the color of the top edge, but this color defines the color of the left edge. So it's probability 1/2 if I choose green and red at the same time. I don't care about this edge. So the density of this graph is 1/2. And again, by the same arguments, the epsilon density tends to 1/2 too. And the next question, does this graph contain K4? So for my K4, I have to order the edges in some direction. I know that this edge has a color, for example, green. But that means that if I want this triple to be an edge, I have this edge should be green, and if I want this triple to be red, to be an edge, means that this edge is red, and you see the problem. So you can't color, or these three vertices will never be an edge anymore. Yeah. So how did I define the edge set of this graph? So I somehow defined a function that gives each pair a color. So in my case, either red or green. And then the edge set of this hypergraph are triples such that xy, xz, so the left edge, the top edge, and the right edge are good. And whatever good means, so I can just define my set good. The subset of the color, always picking three colors. And then I can say that good basically means that this is in my palette of good colorings. Okay. So getting back to this example, what's the color set I could use? basically arrows that go in one direction and arrows that go in the other direction. So each pair can be colored by one of those. And then the good colorings are this one. So that's the left edge, that's the right edge, that's the top edge bringing it back. And this one. And the epsilon density of the graphs are more or less almost sure. The size of my colors divided by all colors to the 3. And by doing so, you can obtain lower bounds. So you might ask, or think, what is the smallest value you can obtain by this coloring scheme argument? So taking 3 colors makes this value smaller. Taking 4 is more or less nonsense if you choose only one set here. Okay. So I want the color set to have size 3 to make this value smaller. So we get more efficient writing. And we choose here 1, meaning so the palette might be, choose the left edge blue, the middle edge or the top edge green, and the right edge white. So that's the smallest value we can obtain by all this principle. So what do we know? The graph F has no ordering of the vertices. Such that we can color the pairs. Of the vertices, such that each edge of F agrees with exactly this picture. So if that's the case, then we know that the uniform Turán density is at least 1/27. So just pick a line of vertices, you randomly color, uniformly randomly color with 3 colors, and you say, if you observe this, this is an edge, and otherwise it's not. It's epsilon density 1/27, and it's F for you. Because you cannot color F, or cannot find a coloring of the pairs of the vertices of F so that it agrees with this here. And what if it's the other way around? So if F has an ordering of vertices such that we can color the pairs of vertices so that they agree with all of this. Then we know that this value is smaller than 1 over 27. And actually, it is 0. And that's a result by Reiher, Schacht from 2016. So you see these three guys like to work together. Yeah. Okay, so we have seen that there are graphs that are 0. You don't obtain any value between 0 and 1 over 27. So you may ask, is 1 over 27 possible? And that is a result by Gabe, Kral, and my son. So there exists hypergraph with uniform Turán density 1 over 27. And that are all the results that are known so far. So if you have your favorite graph you want to obtain the uniform Turán density, you're the first one. If it's not covered in this case and if it's not 0. Okay, so I promised you to speak a bit about cycles. So why is it interesting to speak about cycles? Yeah.
Is F exceedingly mysterious?
No.
Okay.
They works. You add. There are not enough colors for this. So you add a kind of another color. Guess it works this way, and you either choose the normal tuples like this, or you have this prime color on it. I actually know that that's the same, and I start 2 colors and I choose blue as the color that can be on 2 positions. So either it looks like this. So that are the 2 color schemes, and you see on this edge you have tiny bit of possibilities to overlap those 2 cycles.
I see.
And those graphs give exactly 1 over 27. But it's an implication from here to here. So it's not clear whether all graphs with 1 over 27 can be obtained this way. So that's another open problem.
Thank you.
You're welcome. So as I pointed out, the big question is K4. So what can we do to make our life a bit easier? Either we kick out one edge, but that's solved. And arguments are not directly hyper for this. So another possibility is more or less put another vertex inside here. And then we have these edges, and then we, in the obvious way, bring it together. And this graph is a cycle on 5 vertices. So you see it's more or less a kind of a generalization of the K4. So we can ask about the C5 cycle, and if we do this, we can also do all the cycles, or ask about all the cycles. Good. Lower bounds for the C5. Let's do it with the coloring scheme again. So I need colors and I need good tuples. And as colors, I like to use blue and two different kind of reds. So let's call it light red and dark red. Maybe a dark red. I guess you know what I mean. And then the good tuples are those with the left is red and the top one is red. And the last one is blue. So, and those red mean either light red or dark red.
Do they have to be different from each other?
No, they can be the same. So what basically gives us that graphs obtained from this have epsilon density. We have, this set has basically four patterns, and we have 3 colors, gives us 427.
Wait, sorry, are you just saying color it red with a higher probability than blue?
That's the other way to say it, yeah.
Okay.
So either you color red with probability 2/3 and
Okay.
blue with 1/3, or if you want to adapt it to this uniformly colored color scheme I was presenting before, you cheat on this to get this coloring. So what do we know about the uniform Turán density of cycles? So cycle means for me that n is at least 5. 4 is not a cycle, 4 is a complete graph. So it's at least 4/27 in this case. But assume you have a 6 cycle or a 9 cycle. So let's say 6 cycle, then I can put 1 here, 2 there, 3 there, 4 here, 5 here, 6 here. And continuing like this, it becomes a 9 cycle or so on and so on. And then I put all edges between here blue, all pairs between here red, and pairs here green, and I don't care about the rest. So this graph has a coloring as I presented it here. Means that the uniform Turán density is 0. In the case that 3 divides the number L and 427 not. It's straightforward to show that this does not work if L is not divisible by 3. Yeah. So what do we have here? One can say that we have 3/4 of the conjecture. We know it's equally 0 in this case, and we have a lower bound here.
Oh, you established that it is equal to 0, 3 divides out?
Yes.
Because of this theorem?
Because of this theorem already here. Yeah.
Okay.
So there's a lot of work in this theorem.
Mhm.
Okay, and what is possible? So actually we have equality here, and that's a result Mattia, he was a PhD student in Zurich and is now in Princeton. Jay Cooper, he is a PhD student in Brno of Dan Kral. Dan is involved, I am involved, and what's his name? And David, he is a PhD student of Denis Süderkopf in Zurich, and we could show that there's equality here. Okay. When did I start?
You have like a cut, like 2 more minutes.
I have 2 more minutes.
Yeah.
Then I won't speak too much about this, I'm afraid. Yeah, that doesn't make sense to bring in 2 new definitions. Okay, so things that are important to do this. So you're not considering hypergraphs in general, you consider n-partitioned hypergraphs. And you use hypergraph regularity to show that each hypergraph has or can be interpreted by an n-partitioned hypergraph. And then in this n-partitioned hypergraph, you can more or less find some color rings, so picking some top vertices, left vertices, and right vertices. Pick the good one, apply a lot of Ramsey theory to get rid of everything in the graph that might do some problems, and end up with a small graph where you basically find exactly the cycle. Yeah. In this paper, we needed 37 lemmas to do so. It's super technical, a lot to do. Yeah. So, but basically, the word is bring it up to n-partitioned hypergraphs. That was more or less the same that those 3 guys did for this. Good. So I hope I could show you why it's important, or why it's worth to consider uniform Turán density. Uniform Turán density only works in a hypergraph case. In the graph case, if you have an epsilon density somewhere, you can use the regularity lemma, and you find the clique in the whatever size you wish, and you're done. So that's not working in this case. Uniform Turán density more or less struggles again with the same problem of we don't know what's K4. We believe that the lower bound is a good one, but as long as it's not proven, it can be everything. And there are a couple of results. So K4 minus is done. There's a characterization of those is 0. A few results when it's 1/27, and our new result about 4/27. This paper, I hope we can submit it to, or bring it to archive very soon. Still some work to do. Has a couple of nice ideas that can be used to obtain new results, but let's see what time it brings. So, thank you all for listening.
Thanks, Andy. Are there any questions for Sam?
Okay. So you say you had 37 lemmas?
Yeah.
And I'm guessing that they call hypergraph regularity itself as a black box or something, right?
Yes.
Okay, so that itself is 37 lemmas, right? That's
Yeah.
highly technical too.
So basically, we are not using the regularity black box. We're using this n-partite hypergraph black box from their paper. So
okay.
it's a black box in a black box.
Yes, yes. Yeah. Is the denominator always going to be 27? Because Chris brought up this idea that you have probability 2/3, 1/3. So what's stopping you from picking these colors with probability, 0.37 and 0.63 or something?
If you pick it another way, you do better.
Okay.
That's more or less. So in this case, if I have only two colors,
Mhm.
I optimize the density if I choose the red one with 2/3 and the blue one with 1/3.
Okay, and it's always going to have that sort of, if you do it this way,
Yeah.
then it's going to have that sort of result. the
Yes.
minimum curling. Okay.
That's actually another super nice conjecture. So the conjecture is that every uniform Turán density can be obtained from some amount of colors and some palette of colors. I mean, the lower bounds work this way. Showing upper bounds,
The only
It's-
problem is the conjecture is that the number of colors is not bounded.
Yeah.
Do you happen to remember the basic citation for this random tournament? I forget, get kind of confused. So,
this
I thought it was due to Ferretti, but maybe I heard incorrectly. I mean, this is way back in the mists of time. It proved something else.
I guess it was to Rödel.
Good, okay.
At least Reiher says it's
It's-
to Rödel.
Okay, that's
But-
could be, yeah.
But they're best friends, so I don't know.
So I don't know how much this question has been studied beyond these few people, but, I mean, does this get around some of the computability issues with hypergraph Turán? Like hypergraph Turán is an undecidable question,
Mhm.
right? Does this get around some of those issues?
What means undecidable?
If I ask, here's a 3 uniform hypergraph or 3 or higher uniform hypergraph, and I ask the question, is the Turán density smaller than blah? That there is no algorithm that will answer that question. It is like a halting problem, it's undecidable. So
So-
this is why you, hypergraph Turán is hard, and I'm curious if this gets around some of those issues. Just because you're
Maybe,
enforcing like
maybe.
a uniformity across
So
the
it's
board.
it's
So you can't
it's-
nest hidden things as easily.
it's easy if you fix your F to compute whether a particular color scheme with a certain
Well,
amount of
that's-
colors work.
Okay, well, but that's
So-
for density 0, right? I mean, density 0 is easy to tell in
Uh,
hypergraph Turán.
I mean, if you fix your C and your P,
Uh-huh.
then you can more or less.
So that's.
Okay, this is always the question: what are you parameterizing? But you can basically check all possibilities for F.
Uh-huh.
So, in assuming that you don't want to use more colors than you have edges, and you don't care too much about the work you put to F, you can find your best coloring and your best color palette for this.
Sure,
So,
so
I-
assuming the conjecture, you're slightly closer, except for the fact that everything could be unbounded.
Yeah.
So it's still might not actually be getting around some of these issues. Okay, I mean, okay.
Maybe.
It's interesting.
Yeah.
Yep, well, let's thank him again.
Thanks a lot.